Is there a technology that can electrolyze seawater and use it as hydrogen fuel? Researchers in South Korea have successfully developed a technology that allows for the cost-effective production of high-purity hydrogen by electrolyzing seawater. Since seawater consists of water and chloride, electrolysis can yield hydrogen and oxygen. However, direct electrolysis of seawater can lead to the generation of chlorine, which may damage the electrodes or have environmental implications. Therefore, a technology is needed to inhibit chlorine generation and promote oxygen generation during seawater electrolysis. A team led by Dr. Sung Mok Choi and Dr. Ji Hoon Lee from the Energy Electronic Materials Research Lab at the Korea Institute of Materials Science achieved this by controlling the hydrogen ion concentration in seawater through ion exchange membranes and using nickel-doped iron hydroxide catalysts. This approach effectively suppressed chlorine generation reactions while facilitating oxygen generation reactions. Remarkably, they achieved high hydrogen production efficiency even when using non-precious metal catalysts. This research contributes to the advancement of technology for electrolyzing seawater to produce hydrogen fuel. Since seawater is one of the most abundant resources on Earth, harnessing it in this way can expand the reach of green hydrogen and promote the growth of a hydrogen-based economy. So, rather than generating chlorine by directly electrolyzing seawater, wouldn't it be possible to first convert seawater into water vapor using electricity obtained from natural wind or tidal power generation, collect it again, make pure water, and electrolyze it to produce hydrogen without environmental pollution? The method of converting seawater into steam and then electrolyzing it is one of the ways to produce hydrogen without environmental pollution. However, this method has several drawbacks. Firstly, a significant amount of energy is consumed in the process of converting seawater into steam. Since seawater consists of water and chloride, it needs to be heated to a temperature higher than the boiling point of water, 100, to transform it into steam. During this process, chlorine can evaporate with the steam or be converted into hydrogen chloride. This means that chlorine may be released into the air, leading to environmental pollution. Secondly, energy is also consumed in the process of collecting steam and turning it back into pure water. To liquefy steam, its temperature needs to be lowered or its pressure increased. This requires heat energy and results in a loss of energy that could be used for electrolysis. Additionally, when liquefying steam, chlorine or hydrogen chloride may also liquefy, necessitating multiple purification steps to obtain pure water. Thirdly, the method of converting seawater into steam and then electrolyzing it is more costly compared to directly electrolyzing seawater. This is because the former involves two energy conversion processes, leading to lower energy efficiency. Moreover, the equipment required for liquefying and purifying steam, as well as for electrolysis, contributes to higher facility costs. Therefore, while the method of converting seawater into steam and then electrolyzing it offers a way to produce hydrogen without environmental pollution, its significant energy consumption and costs pose significant challenges. To address these issues, improving the direct electrolysis of seawater may be a more efficient solution. So does that mean that seawater contains not only sodium chloride but also hydrogen chloride? In seawater, in addition to sodium chloride, there is also a component of hydrogen chloride. Hydrogen chloride is a substance formed when water reacts with chlorine and is present in seawater at a concentration of approximately 0.01%. Hydrogen chloride is an acidic substance that plays a role in lowering the pH of seawater. When seawater is electrolyzed, hydrogen chloride can be generated as chlorine gas, and when seawater is turned into steam, it can evaporate or be converted into hydrogen chloride gas. Do hydrogen chloride gas or chlorine gas also play a role in depleting the ozone layer? Hydrogen chloride gas or chlorine gas plays a role in the depletion of the ozone layer. When hydrogen chloride gas or chlorine gas reaches the stratosphere, it is broken down into chlorine atoms by solar ultraviolet radiation. Chlorine atoms then react with ozone, forming oxygen molecules and chlorine oxides. Chlorine atoms are regenerated in this process and can react with ozone again. Through this cycle, a single chlorine atom has the potential to destroy thousands of ozone molecules. Hydrogen chloride gas or chlorine gas can be generated when seawater is electrolyzed or turned into steam. Additionally, artificial chemicals such as fluorocarbons and chlorofluorocarbons also contain chlorine and are known as major contributors to ozone layer depletion in the stratosphere. The ozone layer plays a crucial role in absorbing ultraviolet radiation, protecting life on Earth. Ozone layer depletion can lead to an increase in ultraviolet radiation, resulting in health issues such as skin cancer, cataracts, and immune system suppression. Therefore, efforts to reduce the emission of ozone-depleting substances like hydrogen chloride gas or chlorine gas, and initiatives for ozone layer recovery, are essential.